So in the next few lectures, we're going to discuss the topic of delegating quantum computation. And before we get there, I want to ask a question. The question is, what are quantum computers going to be good for? It may seem like a very naive question. Of course, they'll be used for quantum algorithms, quantum cryptography, but in practice, how will these quantum computers look like and how will we interact with them? What are the kind of tasks that they'll be most useful for? This is a question that was already asked by Richard Feynman, who was a professor of physics at Caltech. And Feynman is credited as one of the inventors of quantum computing. He was the first to foresee the possibility of using quantum mechanics to implement certain procedures or certain algorithms much faster than you could classically. But Feynman's insight was that whatever quantum computers are, they're likely to be very special purpose machines. They will have some advantages, but in many respects they'll be much more costly, much less stable than conventional computers. And where will they find their largest advantages? Precisely in a certain way what they're built for, which is simulating quantum systems, performing physical simulations. In one of the most important applications for quantum computers, which is just to simulate quantum systems, because these are precisely the kind of systems for which, if you have a quantum mechanical machine, then you can gain a large advantage. Now, how far are we from this? Let's see the kind of quantum computers that we have today. And here are a few pictures. These are all different types of quantum computers. They range from 3, 5, or more, 128 qubits here, built in different labs across the world. And they're all based on different architectures. This is why they all look so different, because researchers have a lot of different ideas as to how they could build a quantum computer based on superconducting qubits or trapped ions or all kinds of possibilities. So now, you can't see from the pictures so well, but these machines tend to be very costly and very bulky. It's unlikely that one is going to land on your desktop any day soon. But these exist though. They are being manufactured and they exist in the physicists' labs or at some startup companies. And the question is, how do you use them and how do you trust them? What you can imagine is that if you want a certain algorithm or a certain simulation to be performed, you'll ship the data, the instructions over to the lab, to the server, and you'll ask the server to perform the computation for you. In fact, this is something that you can already do. IBM has a quantum computing in the cloud initiative based on this exact computer that I gave a picture here of you, the 5-qubit computer. You can go to the IBM website and you can program that computer, ask it to run a certain algorithm. But then how do you know that the computer is actually running the algorithm that you're asking it to? If it's a small algorithm on 5 qubits, then you can write down everything, the state of the algorithm, do the simulation yourself, and check the results. But then if you can do the simulation yourself, there's no good reason to use the quantum computer anymore. So suppose that you have a good reason to use the quantum computer because you want to use it to generate predictions for a quantum system or implement a quantum algorithm that you can't generate yourself. Is there a way for you to do this, given that you yourself do not have access to a quantum computer, in a way that you would be able to verify the results that are provided to you by the quantum machine? So that's the problem of delegated computation. To set it up a little bit formally, this is the kind of scenario that we want to consider. It's a scenario that's going to involve two parties, the verifier and the prover. The prover we sometimes call the server. So the verifier has as input a certain string, x, this is just a classical bit string, and a description of a circuit. This is a quantum circuit, but whose description is given classically, just as the list of gates and which bits the gates should be applied to, which qubits. Now the verifier is classical, so he has this input, this circuit, and he wants to evaluate the circuit on the input but can't do it himself. So for this he can talk to the prover, send information to the prover, and this prover here will assume has access to a quantum computer. So this prover can run quantum circuits, it can create states psi, and it can apply gates. It can apply a Hadamard gate, it can apply a Toffoli gate, it can apply Pauli gates. So let's assume that this prover can perform universal computation. And so the question is whether this verifier, who we assume is a trusted party, this verifier just wants to execute the quantum circuit on the input, can delegate the execution of this circuit to the prover. So that's the task that we want to achieve. Now let's define the kind of properties that we want to be satisfied. So the first property is the usual one. We want a protocol that is correct, which means that if the verifier performs what it's supposed to do, if the prover behaves as a honest prover in the protocol, then it should be the case that whatever goes on in the interaction, at the end, the verifier produces a result which is equal to the outcome that you would have obtained if you had run the circuit on the input and then measured the output qubit to obtain a classical output C of x. This is just a single bit output of the circuit. Okay, that's correctness. Then we want some cryptographic properties. So what kind of properties do you think we might want? There's a couple that I think are important. The first property is called blindness. And this is the property that informally the prover doesn't learn any information about the computation that the verifier wants to perform. This would be the case if you imagine that, for instance, Amazon is holding this quantum computer and you're delegating some important computation to Amazon. It might involve your credit card number, or it might involve some secrets. So you want Amazon to execute the computation, but you don't want them to learn either what the computation is or what the result of that computation is. So this is the blindness property. And then another property is verifiability. Of course, you want that if the prover is dishonest, then either still for some reason you manage to get the correct outcome, or you're detecting that this prover is behaving dishonestly, is not implementing the circuit that you're asking it to implement, even though it doesn't know what circuit you're asking it to implement in case the protocol is blind. So that's verifiability. So verifiability and blindness are two different properties. Neither implies the other. It will often be the case that verifiability does imply blindness though. The reason is that very often, how are you going to show verifiability? You're going to argue that the prover, the server, can't distinguish between different kinds of tests that you perform on it. For instance, you could test this server by asking it to run the identity circuit. And then you can check the outcome. The outcome should just be 0, the same as the input. Nothing has happened. And a natural way to achieve this is by having a protocol that's blind, so that the prover cannot tell the difference between the verifier asking it to apply the identity circuit or a generic quantum circuit. So the main way in which we'll end up proving verifiability is by going through blindness first. But it need not be the case, and both properties can hold independently of the other, and both are interesting to have. And now the last set of conditions to consider is how efficient the protocol is. Because after all, the whole goal is to save time to this verifier. It cannot execute the quantum algorithm by itself, otherwise this is what it would do. It cannot do a classical simulation, because otherwise it would do it. So we want this interaction with the server to save time. So in the best of worlds, we'd have this verifier be a purely classical polynomial time, possibly randomized machine. This is what we'd like to achieve. Unfortunately, as we'll see in the coming videos, we can't always achieve this, and sometimes we have to assume that the verifier has limited quantum abilities. For instance, we could ask that the verifier is able to prepare single qubits, one at a time, in certain bases, say the computational and the Hadamard basis. Maybe we might need the verifier to be able to implement very simple measurements. Asking a little bit more, we could ask this verifier to have a large quantum memory, but maybe a memory on which it cannot perform arbitrary operations, just to store qubits for a fixed amount of time. So you'll see in the next videos, we'll sometimes make some of these requirements, not always. It's important to keep in mind that the main goal is that whatever abilities we require of the verifier, they should be lower than what is needed in order to execute the circuit that it's delegating. Now, there's also conditions that we could require on the prover. This prover is supposed to be implemented by IBM or Amazon. We don't want to design protocols that ask too much of these provers in order to obtain security, because then they won't be able to do it and we'll be stuck with our circuit that we can't evaluate. So again, ideally, the prover will be this time quantum, but still polynomial time. We don't want to ask it to perform computations that take more than polynomial time. It might be the case that we want to put additional assumptions on limitations of the prover in order to achieve security. We'll see about that. And another different assumption that we'll use later on is that it might be useful if the verifier is able to interact with not one prover but two provers, such that these provers are spatially separated but maybe they share quantum entanglement. So we'll see that this can be a useful way to perform delegated computation by using the two servers to check the one's answers against the other. This is something that we'll see a little bit later. So I've told you about delegated computation, about the correctness and cryptographic requirements, and about the efficiency requirements. And now in the next 3 videos, we're going to see 3 different ways of achieving delegated computation. None of them is going to be perfect. Each of them is going to have its advantages and its inconvenience, and each of them will be interesting because it'll demonstrate a different type of cryptographic technique.